Swayam Prabha. Digital India. Educated India.
Okay, good morning. In today's class we look at conduction with change of phase. It is a very important problem from an engineering point of view, and it also involves some tricky mathematics. So we will just see how far we can go in this. So as you can very well imagine, melting and solidification take place in a variety of situations in life. Okay. Melting of ice, making ice cream, okay, processed food, dairy industries, okay, then preserving the blood in the blood bank. There are many applications, from just my ice cream making to so on. Melting and solidification and freezing, they occur in a lot of applications. As far as metallurgy is full of, melting and solidification, okay, where depending on the heating rate, heat treatment is of course heat treatment may not involve the change of phase, sometimes it may involve. Otherwise in metallurgy also they have phase transformation, austenitic stainless steel, martensite and so on, and so they are obsessed with this melting and solidification problem. As far as heat transfer is concerned, more than melting and solidification, change of phase from liquid to vapor and vapor to liquid frequently occurs in heat exchanges. Okay. So heat transfer, you have heat exchanges. Most importantly, latent heat storage devices. You want to store solar energy using phase change material, okay, using paraffin or something. So what will happen is, you collect the sun's rays, you heat water, this water is circulated in a tube, in tubes inside a tank. In this tank you have got some paraffin or wax or something, the heat is transferred to this. So from solid it becomes a liquid, so it stores like this. Then during the night you again send same water through these tubes, but that water will be cold water and it will get hot, you will get hot water. So may sir, what is the big deal, why do you want to complicate things, why do you want to use paraffin, wax and all that? The simple logic is, the melting heat is, the latent heat is much more than the specific heat, and latent heat transfer takes place without any temperature difference. Is it it's isothermal. So from the second law from a thermodynamic point of view, it is the most efficient way of transferring heat. In fact, the goal of heat transfer is basically to reduce the delta T. In fact, we want to maximize the heat transfer performance, we want to keep on increasing H. Why? Because Q is equal to HA delta T, right. So if Q is fixed, we want to keep on increasing H so that delta T comes down. Okay, if you are able to accomplish the heat transfer at delta T is equal to 0, that is the best you can hope for. Okay, so this energy storage with phase change materials offers that opportunity. So energy storage, welding, casting, all your foundry business, casting, and then you pour some hot liquid into the mold, then you get the object you want, aluminum casting, die casting, all this. So casting and welding, so in all these applications you have conduction with change of phase. Okay, therefore it is important to know, to model conduction with change of phase. Up to a certain level we can analytically model, beyond that we have to numerically model. Okay. So, what are the key points? Let us consider a situation where there is a solid, the whole solid is at a temperature Tm, Tm is the melting temperature, of course it is infinite in this direction, it is also infinite in this direction, therefore it is known as the semi-infinite. What is a semi-infinite solid? Only the left side is specified, right side is infinite. Sir, how can you get semi-infinite? Semi-infinite means the amount of the region in which this melting activity or heat transfer activity is taking place in relation to the dimension of the body is very less, that is why it is semi-infinite. Okay. The body is 30 centimeters thick in thickness, you are talking about the first few millimeters where this melting has started, you are still talking about the early regime of transient conduction. So it is semi-infinite. What is semi-infinite? What is the semi-infiniteness there? Most of the body will not know that some disturbance took place at the left boundary, so it will continue to sleep at its initial temperature, that is semi-infinite. Slowly it will get affected. Are you getting the point? This is we have discussed earlier in this course also, where I have explained delta, the penetration depth, how much the thermal disturbance will propagate, and then delta can be, you can use the similarity variable x by 2 root alpha t, all that we have discussed. Now let us say that suddenly left side you raise the temperature to T naught. So this Tm, everything was a, previously everything was a solid, T naught is greater than Tm. So and x is like this. Is the situation clear to everybody? So where will the melting proceed? Tm is the melting temperature, T naught is greater than Tm, so the melting will start from the left to the right. So here you will have liquid region. Now a simple since this was at Tm, since it has not melted, it will continue to be at the temperature of Tm, and here it is T naught, the temperature will decrease like this, correct? So this will be the temperature profile inside the semi-infinite solid when melting takes place. Okay. What is the key engineering result we are trying to seek? The key engineering results we are trying to seek in the problem of melting and solidification is, number 1, what is the position of this interface with time? What is the interfacial velocity? That is, how much is the melt, how fast is the melt front moving from left to right. Second, once you have captured the melt front, within the melt front how is the liquid temperature changing with x for various instants of time. Okay. So these are the key engineering results. Therefore the interface is not fixed, the interface, if this is the interface, so the interface is a function of time. We want to know what this S of t is, that is a key engineering result we are trying to seek. Okay. What are the key points? First, whether Tm is a single temperature, or there is a region, there is a range of temperatures about which the melting takes place. That means it starts at 37 and ends at 39, then we are in trouble. Then you won't have such a sharp interface, you will have some mushy region, half melt, half liquid, 25% melt, 75% liquid, like that. Then you have to model that mushy zone also. Obviously you can very well imagine that if you have a situation where Tm is not specified at one point, there is a small range for Tm, then it is much more difficult. Okay. So whether Tm is a single temperature, yes, for pure substances and eutectic alloys. Okay. If answer to A is yes, then we have a sharp interface, correct. There is a sharp interface, left side is liquid, right side is solid. Okay. That is issue number 1. Obviously in this course I am going to consider only a pure substance or eutectic alloy which has got a sharp interface, only one melting temperature. Then so this is also called the interface or the melt front, freeze front or melt front. At the interface temperature is continuous, correct. Whether you are approaching slightly from the left side or slightly from the right side, the temperature will be Tm, but heat flux will not be continuous. Okay. This is a major difference between the normal conduction which you study and this and conduction with change of phase, because lot of people will think, sir, what is a big deal if there is a melting which takes place, there is an additional resistance, okay, it can be treated like an additional resistance because there is a finite amount of heat involved in melting and then the solid will become liquid, then you can continue with the process. Why can't you add that melting, model that melting phenomena as a contact resistance and have a resistance network and proceed. You cannot model the melting and solidification with simple formula, with simple approaches which you learnt in conduction without change of phase, basically because minus k dt by dx from left side is not equal to minus k dt by dx on the right side. Minus k dt by dx on the left side is equal to minus k dt by dx on the right side plus whatever heat is generated because of the whatever heat transfer or energy transfer takes place because of the phase change, that we will model. That is the first thing we have to learn, that is developing of the interface condition, that is called the Stefan condition. Stefan found this out. How do we model this? Okay. So is the situation clear? So the key differences are the temperature is continuous, heat flux is not, and Tm need not be a single temperature, there could be a range, then you have a mushy zone, that means you have some region where the melting starts, some region where the melting ends. Okay, that is much more difficult to solve. It can be modeled using software or you can write your own codes, but if you do not worry about that, consider a single temperature which is okay for pure substances, eutectic alloys, you can attack the problem analytically. Okay. Now we have to get this interface condition, that is very critical. Shall I erase this? Okay, let us consider this itself. Now let us consider this interface. Consider a thin slice control volume around this interface. We are going to study the story around this control volume. So there are several ways in which you can consider this. Now we can assume, we can you can use a control volume, you can use a Lagrangian approach or an Eulerian approach, right. to figure out what? To figure out the state of affairs happening within the control volume. There are two things which are taking place. There is a transfer of mass and there is a transfer of energy. So you have to model this transfer of mass. Now we can assume that the interface and the control volume surrounding it are stationary. One possibility is to assume that the interface and the control volume surrounding it are stationary, but material is just coming from left to right, or material is coming from right to left. For example, material is coming as solid from the right, entering the control volume as if it is some process, as if it is some machine. Material is coming from left, getting melted, exiting as liquid. Okay, at a particular instant of time. Okay, since the control volume is not expanding in size or contracting, it is a fixed area. Now what can you say about the mass balance across the control volume? Mass conservation you can consider the area of cross section to be A. So rho L, rho S, A is the same, then velocity. What is this velocity, sir? What is this velocity? This is that velocity which is actually the velocity of the front. Okay. Now what can you say about this? Now rho L VL into A is equal to rho S into Vs into A. So what is the funda here? If rho L is different from rho S, rho L is different from rho S, okay, in a particular instant of time 5 centimeters of solid thickness may translate to 7 centimeters of liquid depending on the density. That is what I am trying to say. If both the solid and the liquid phase have the same density, it will get cancelled, does not matter, but when it melts the density could be changing, but the mass has to be conserved. So we should not make the fatal assumption that the velocity at the liquid side must be equal to the velocity at the solid side, but rho L VL equal to rho S Vs. Okay, is that clear? Of course many materials rho L is equal to rho S and we knock it off, then we do not worry, that is another story. Okay, now rho L VL is equal to rho S Vs. So that is the first, it is okay, that is point number 1. Now energy balance. If you consider from the left it enters as liquid, oh sorry, from the right it enters as solid and goes out as liquid, that is a melting problem, or from the left it can enter as L and go out as solid, that is the solidification problem. Okay. So when it is coming, there is a flux, the conductive heat flux, which is coming because of a temperature difference. There could also be a conductive heat flux here, I am just saying that it is at Tm. Initially it need not be at Tm, it can be at some other temperature. Then there could be temperature gradient within the right side also. I started the lecture to make it clear. So there could be conductive heat fluxes on both sides. Then this liquid is coming with an enthalpy of HL. This solid is coming out with an enthalpy of HS. Therefore the energy balance demands that whatever is conducted in plus whatever enthalpy is brought in must be equal to whatever conducted out plus whatever enthalpy is taken out, correct. So these two are critical, right. Now how can you do this? Q okay. What is Q connect minus K? Dou T by dou X, okay, into A you want to take, or A you can cancel, or you will cancel, plus rho S you put it as rho L, okay, rho L is convection. We treat it as convection, enthalpy, no, that is enthalpy, liquid enthalpy. So this is equal to minus K solid dou T by dou X, this is liquid and solid, see sometimes I may use small s, you be consistent, L is liquid, S is solid, plus A, I am coming to HFG, don't jump to conclusions. Left side is L, right side is S. Now I am saying that HL minus HS is HFG, I am coming to that. Because when it is coming with the liquid left side, across the control volume only this transformation takes place. I cannot straight away put HFG when I derive. What is the fundamental principle? How do you get that equation if you ask? Suppose I straight away write minus KL dt by dx is equal to minus Ks dt by dx plus HFG, you will ask me, sir, how? I am explaining how that HFG is coming, okay. Now we can do what you are saying, so minus KL of the liquid is equal to so usually the solid has more enthalpy than the liquid, or HL minus HS, what do you do? HS minus HL, that is what you want to do, okay. Now what is the beauty? Rho S Vs is equal to rho L VL, okay. So this is that is your HFG, we do not say HFG because HFG is for water to I put HS minus HL, is that correct? I knocked off the A, okay, is it correct? Okay, this is called the interface condition, very important. Now are you confident that HSL is positive? Are you confident that HSL is positive? That is why I am also, no, there is nothing wrong in what we have written. That is why is that correct, or did I make many mistakes? Plus okay. Now HL minus is this correct? That is why I do not want to get a negative value. Will that HLS be positive or? Yeah, because that is no. No, HFG means fluid to Hg minus Hf, gas to, so liquid to solid. Yeah, liquid will have more enthalpy. That is why if you bring it like this, it is Hs minus Hl, we call it as HLS, we put a minus sign. Now it sets it to rest. Okay, this is called the interface condition. Now you have to solve the conduction equation with this interface condition, that is the added thing. So the first half an hour what we did was we derived this interface condition. Without this interface condition you cannot proceed. Okay, right. Now what about the interfacial velocity? The VL can be considered to be ds by dt, where S is the location of the interface, where S is the location of the interface. Therefore this is the interfacial velocity. So apart from the time which enters the unsteady conduction, the time enters the interface condition. Okay. So now this condition we have to use. So equation 5 is valid for both melting and solidification. If you want you can write equation 5 is valid for both melting and solidification. Now let us consider the Stefan problem. What we considered a little while ago is the Stefan problem. So consider the melting of a semi infinite solid. The whole of the solid is at a temperature of Tm, which is where Tm is the melting temperature for times T less than or equal to 0 or up to time T equal to 0. Now at time T greater than 0, at T greater than 0 for x equal to 0, T is equal to T naught. T naught is greater than Tm. That is, the left boundary's temperature is raised above the melting temperature. Therefore melting has to start in the solid from left to right. Okay. Now as time elapses the melting proceeds from left to right. Now we have to solve for the conduction, we have to solve for the conduction in the solid. Beyond this region it is only solid which is at a temperature Tm. So I do not have to solve the equation of conduction inside the solid, I have to do it if there are temperature gradients within the solid, but fortunately for us there are no temperature gradients because that continues to be at Tm, it is the initial stages of melting and this is going to be at Tm only. Therefore we have to solve only the conduction equation only on the left side of the geometry. Okay. So for the one dimensional conduction in the liquid region, so for the one dimensional conduction in the liquid region the governing equation will be the governing equation will be 1 by alpha so we call it as equation 6. Yeah, alpha no, yeah we will call it alpha L is better. Okay. So this is the transient one dimensional unsteady heat conduction equation which we are aware of. It supports two boundary conditions in X and one initial condition. Okay. So the initial condition is for all x t equal to 0 t is equal to Tm. So one initial condition and one boundary condition are given. What is the third boundary condition? T S is like this spatial coordinate, t is the time, at any time at t of s t equal to Tm. Therefore the solution can be worked out only up to s, the solution can be worked out only up to x equal to s. Now the difficulty that arises in the problem is s is not known for us because s is a function of time. Therefore s has to be obtained as a part of the solution. In fact how s changes with time is the key engineering result which we are trying to seek, because from an engineering point of view how fast or how slowly the melt proceeds is an information which we are seeking. Okay. So therefore we want to know, we do not know what this we don't know what this S is right now, but now one thing is very sure is in order to find S one more condition is required. That one more condition comes from the interface condition. Okay, yes. Agreed. Now in that interface condition, what is dt by dx of the solid? Is there any temperature gradient in the solid? No, because the whole solid is at Tm, therefore the interface condition can be simplified for the Stefan problem. Okay. Now for this problem, because there are no temperature gradients within the solid continues to be at Tm. Okay. Therefore minus KL no rho minus or plus?
Minus rho L
Okay, plus
rho L HL into ds by dt.
That's it. No, we have not solved it, but
From this you get S.
it's not so easy, so we will see that therein lies some fundas are there. Now we have correctly formulated the problem. Now there is nothing wrong in the formulation, whatever physics is there, whatever mathematics is there, we have incorporated. Now we have to seek a general solution to the problem with the boundary condition, initial condition and the interfacial condition. We have to find the solution to the Stefan problem. Now this is a conduction in a semi infinite solid, do not worry about the melting front and all that. As far as the left side is concerned, it is basically conduction in a semi infinite solid, that is the initial portion. For the initial portion I have told you that we can introduce a similarity variable, though I may not have worked out the full similarity solution in the class. In the course I have already told you that x by 2 root alpha t can break down this, can convert this PD into ODE and you can get a solution in the form of an error function. Okay. So the general solution to 6 is given by T of x comma t I do not have time to derive that here, but it can be shown that once you have eta equal to x by 2 root alpha t, you can substitute for eta here and then this will convert into ODE, and then in just another 10 or 15 minutes you can show that the PD is converted to ODE and the solution for that ODE is given by the error function. Okay. Now the error function of x is given by 2 by root pi don't worry, right hand side that integral, the variable under the integral sign can be anything, it can be alpha, beta, gamma, it is a dummy variable because you are substituting 0 to eta. Okay. Now, so this is 11. Now slowly one by one you have to get the constants A, B as well as S. Okay, we will do that slowly. What is error function of 0? Error function of 0. Integral 0 to 0, error function of 0? 0. At x equal to 0, what is the condition? T equal to? Error function of 0 is 0, therefore this term vanishes, therefore A must be equal to T naught. Okay. At x equal to S, what is T? Very good. At x equal to S, T equal to Tm, because that is the place where there is a melt front of the interface. Now Tm error function of, tell me exactly, error function of S by, correct. Therefore B equal to Tm minus T naught okay. Therefore agreed. Yeah. Tm is known, T naught is known, alpha L is known, time is known. If you give the position of x, it is possible for you to calculate the error function of x. You can solve the problem provided you know what S is, but you do not know what S is. So the problem is not over. You are able to understand that? This solution is valid only up to S. You can work out a temperature profile only up to S. Beyond S, the body is at a temperature of Tm, but that S itself is changing with time. Unfortunately, the solution has S. I do not know what the S is, but I do not have to lose hope because my interface condition is there. So that interface condition, if I substitute my general solution, because k dt by dx is there at the interface, so if we substitute k dt by dx, the only unknown in this is S, left side also I will get s, right side also I will get some function of s, I will get an ordinary differential equation in s. If I solve the ordinary differential equation in s, I can go home. So much for the simple Stefan problem. Okay. Now let us substitute the interface condition and stop. We will work out the solution in the next class. Okay. Now we will just, is this clear? What is the problem? Okay. Therefore, what you have to do is we use equation 10. Yeah, please start differentiating minus KL what is the integral of the error differential of the error function? The differential term goes, so you will have 2 by root by eta square. You are applying at x equal to s. So it is not threatening us. Some error function of s is there, e to the power of s square is there, ds by dt is there. Where is the hope? I want to get s as a function of time. Okay. If you solve equation 18, you will get s as a function of time. The dependence of s on x is gone because we have substituted we have worked out the interface condition at x equal to s. Okay. Fortunately, it is known fortunately s is equal to m of t is known to satisfy the above equation, where m is a parameter which depends only on the properties of the medium under question. Okay. So you can substitute s is equal to m of t there, and then the resultant equation will be put in terms of m, and you solve for m, and then once you solve for m, then you this for m into root t, m into root t is known to satisfy this. So if you substitute s equal to m is equal to root t, the whole thing can be solved and you can find out the solution, and that completes. We will work out the solution in the next class. Okay. So how do we get this? That means what it means is the s goes as t to the power of half, that is intuitive, just like the bond layer, it grows as t to the power of half. Okay. We will see from an integral analysis, we will see how that is actually true, and then we will work this out and get the value of m, solve it, then we will complete the solution in the next class.